Good afternoon, everyone. Can you hear me okay?
Yep.
Okay. Thank you for joining us. My name is Michael Dickens. I'm a research scientist with High Performance Research Computing. Today, we're going to have two parts to this short course. The first part, I'll show you how to access CryoSPARC on the ACES cluster. And then the second part, we'll have another speaker who will go over the hands-on tutorial. So if you have any questions, feel free to unmute yourself or ask in the chat, and we'll address those questions.
Is it reservation open? Can I
Yes.
launch the CryoSPARC now? No, not yet.
Yes, we have a reservation in place. So
Okay, go ahead. Maybe you will go over there or go over that step.
yes. Okay, so in order to run CryoSPARC, you'll need to get an academic license ID, and you can obtain this from the CryoSPARC website. I'll go over the resources and limitations for running CryoSPARC. We'll get started with running CryoSPARC, launch a CryoSPARC session on ACES. We'll talk about group directories, and then in the end, we'll have another speaker that will go over an interactive tutorial with some example image files. So you can get a CryoSPARC license free of charge. Takes about a day to get a response, and it would be good to use your academic email, since this is an academic license, and you'll need this license each time you launch CryoSPARC. You can only launch one CryoSPARC session at a time, and we'll go over that. So here's the website where you can download the academic license if you haven't already. So this course is being recorded, so you can watch it later on our YouTube channel. And then if you don't have an academic license right now, then you can follow along later after the recording is posted. So the ACES resource is a composable cluster, a composable resource cluster. And what that means is that we have some nodes that at one point may have two H100s attached, but then they can be reconfigured to have four H100s per node, and that's dependent on user request. So at any time in these slides, when I show a configuration, if you go to the system, you might see a different configuration. But at one point we had 30 H100 nodes, and each of these nodes had two H100 GPUs attached. If we had 30 H100 GPUs, there are two H100s per node. So that means at this point we would have 15 nodes, each one of them having two H100s. We have 6 A30s, and those currently we have two nodes where each node has two A30s. Then we have 70 CPU only nodes, and there are some other specialized nodes that you can't use, or they're not compatible with CryoSPARC. So whenever you launch your job, just make sure you allow enough processing time for your job to complete. It's good to overestimate how much time you'll need. You might want to launch a job for, we do have limitations based on the whether you're using a CPU only node or a GPU node, and I'll go over those time limitations, but you can go ahead and put the maximum time. And then when your processing is complete, make sure you cancel your job so that you can free up the resources for other users. And if you launch a job, for example, if you launch your job at 24 hours and you're finishing half the time, just make sure you delete your job so other users can use those resources. All right, so you can only launch one CryoSPARC portal session at a time. but within your CryoSPARC session, you can run multiple jobs, multiple processes, and we'll see that later in the tutorial section. There are some tasks such as importing images that don't require GPU. So if all the GPUs are tied up with other jobs and you want to import some images, you can just launch a CPU only job. And the GPU job does get busy at times, and it might take an hour or more for your job to start. In that case, if you're going to be away from your computer and your job hasn't started yet, then it would be good to just cancel your job. Because if you go home and your job starts right at midnight and runs for 8 hours before you get back to the office, then those resources have been tied up for 8 hours without being used. And then if you submit a job, it may be delayed due to an upcoming maintenance, and I'll show you how to recognize when a maintenance is scheduled. So first, what we want to do is access the ACES portal. So we're going to go to our website, hprc.tamu.edu, and then we have this portal tab, and then we're going to click ACES portal for access users. So portal, ACES portal access. Okay. So you might, if you haven't logged into using your access ID yet, you'll get to this page, and then you'll need to select your identity provider and then log in using your credentials. I've already done this, so you didn't see me land on that page, but we'll give you just a minute if you haven't logged in already to go ahead and log into ACES, the ACES portal. And then once you do get logged in, you'll reach the screen like this. So if you can give us a show of hands in the chat, just let us know if you've logged into the portal. We want to see how many users will be using the GPUs today for the tutorial. We will start off by starting a CryoSPARC job. If you haven't launched a CryoSPARC job, the first time you launch it, you will need to launch with CPU only. So you'll put your license ID in there in this field here. We only have one version right now. You need to paste your license ID when you receive that, and then just go ahead and select 3 hours and CPU only. So the very first time you log in, we can go to interactive apps. We'll only see, make sure you select the CryoSPARC short course. If you haven't ever used CryoSPARC on ACES before, you would only have a CPU option. So go ahead and select that one. You can leave it at 1 hour, or you can set it to 3, because we're only going to use it to initialize the data. And then we're going to click launch. That's going to take a few minutes to launch. So I'm going to go on to the slides. So once you launch that job, then you'll be able to log in and accept the license, and then we'll start a second job. So let's go to the ACES shell access. The ACES shell, ACES shell access. So I'm going to go to clusters, ACES shell access. And then what I want to show you is GPU eval. So GPU eval, this is a utility you can use to see which GPUs are available. So if you want to start a CryoSPARC job, you can either launch it on the H100s or you can launch it on the A30s. It doesn't work or hasn't been tested on the PVC nodes. So I recommend, actually we only have options for H100 and A30. So once you reach the command line, then you can type in GPU eval, and it'll show you the current configuration, which may be different from what's on the slide. But you can see right now we have 9 nodes that each have 2 H100s attached. We have 3 nodes that each have 4 H100s attached, and we have 2 nodes that have 2 A30s attached. Then you can see what's available. So if you were going to start a CryoSPARC job right now, you couldn't, and you didn't want to wait, you could probably land one of these H100s. You can see there's one available on node A041. There's one available out of 4, and this one has both available. And you can see how much memory is how many CPUs and how much memory is still available on this node. So you can configure the amount of time, the GPU type based on this output. All right. If you do launch a job for, let's say you launch a job for 2 days and it's still in the pending state, then what you can do is you can come back to the command line and type in the maintenance command. Maintenance will show you if there's a scheduled maintenance. You can see right now there's no scheduled maintenance, but if there's a scheduled maintenance that starts in 2 hours and you schedule a job for 2 days, then your job will remain pending, just because it overlaps with the maintenance window. So if your job's pending for a while, you can also check the maintenance command, but there's not as many maintenance. Most likely it's going to be due to the H100s being used with other jobs than actual maintenance, but also check the maintenance command as well as a GPU avail command. All right, so now I think we've got our CryoSPARC job. So you'll see this blue button here. So this session ID, you can click the session ID, and then you can get the log information in this output.log. This output.log file is a place to look if you have any errors with your job submission. You can check this log and let us know if you have any issues. So we'll go ahead and launch our CryoSPARC session, and this isn't a real email, it's just an email I made up so you can log in. So go ahead and log in and accept the license. You should read it first and accept it. And this will initialize your database. You'll probably see a couple of pop-ups here. Wait just a second. Okay, looks like there's not going to be any. So you can close this window here and then come back to your session here and then delete this job. Yeah, so we want to delete it. And then what we want to do, accept the license, then we want to start a second job or a new job. This time you want to select the H100 node. So let's go back to this CryoSPARC short course. This time you're able to select the H100 node. And we only want to use one H100, so we have enough for all the attendees today. And then make sure you have your license. It maybe have been saved already. And then click 3 hours for the duration of the course. All right, and then click launch. That's also going to take a few minutes to start. So we'll come back to that. And meanwhile, I'll go over some other things. So we also have a utility called Job Stats. And what this does, it creates a usage graph for the CPU percent load, as well as memory used on the motherboard. It also shows you the percent load and the gigabytes of memory used for each GPU that you select. So here's an example. For a job, it's a PNG file. You can see in red, we have percent load here. And you can see really, it didn't, as far as the CPU usage goes, it didn't get even like 10% usage. And the memory was very low. Memory usage was very low here. Less than 50 gigabytes of memory for this session. Now, if you only select one GPU, then another job could be running on the other GPU and motherboard. So you might see stats from the other job. So job stats, as far as the CPU graph goes, is most accurate if you select the entire node, which means if you select two H100s. Now the GPU graph will show you the usage for only your job because only one job will be allocated to each GPU. So in this case, this single GPU job, you can see there's the percent load is in red here and memory is in blue. So you can see there's a spike as you run certain commands, and then there's an idle session while you're setting up your session, your next task, and then you can see there's some processing done as you go through and work your workflow. So you can this is automatically set. Where do you find the images? So for past jobs, you can go to the very bottom of the CryoSPARC launch page. So that would be that's going to be down here. So you go to your data root directory and then go to output. And then we're going to sort it. You can sort it with the newest job on top. And then you can go in here. Actually, I'm going to go to an older job because I may not have any graphs there yet. If I go to okay, here's one. You can see I just ran a job. I didn't actually do any processing, but that's how you find the PNG files. Okay, we do have some group data directories, and if you need to share image files with your group, then you can request that group directory be created, and we will create the directory and give you the path, and then you'll need to specify the path before you launch your job. Okay, so now we're going to go to the second part. This will be presented by Guy Yadav. He is the Cryo-EM Technical Director at the Laboratory for Biomolecular Structure and Dynamics. And so we're going to switch screens here and allow him to share. So if you have any questions about getting your job started, you can ask us now if you want.
So, hello everyone. My name is Gaya Yadav. I'm at Michael Benson. I'm a technical director here at Laboratory for the Biomolecular Structure and Dynamics. Basically, it's the Cryo-Electron Microscopy Center. And today I will walk you guys through the data processing, how we use the CryoSPARC to process the single particle, to do the single particle analysis to get the structure for a protein or protein complexes. So let me share some background. Can you see my slides here or no?
Yes, we see them.
Okay. So first, a little bit of background about the Cryo-EM, and I will not go in depth because we want to finish the data processing workflow. So quickly, I will show you guys what is the Cryo-EM. So the Cryo here, I'm starting with the Cryo-EM workflow, what we need and what steps required and what you need to get the structure. So first of all, you need to obviously do the sample. You need the sample. Sample can be anything, and protein complexes, but there is a size limitations. Uh, you need to make sure your sample is above 50 kD for the smooth processing and also the single particle processing. So as long as it have some limitations, like you cannot go below the you can go. There is some report that's published 35 kb overall size, but it's hard to do, and also only the protein that's very uh, very uh, stable, and you can say like a rock solid proteins. Like, and when if you have that size, you can still be able to get the structure, but it will be harder. So if you have a protein that's larger than 50 kD, it will be easier. So first you need to make sure your sample is as homogeneous as possible. So you do spend a lot of time on the wet lab to make your sample clean and homogeneous, and then you prepare the grid using the vitrobot. We call the vitrification, and after the vitrification, we can do the imaging. We screen the grid, or and then if we can see the nice particles, we can do the data collection. So here, one of the representative image, you can see the black. These are the protein part and the protein particles. Once you see the individual particles separated from each other, and then you can collect large data sets, and then after the once you finish the data collection, you can use the CryoSPARC, relying on the single particle data processing software and get the 3D map. And then afterward you do the modeling using the code, Phoenix, and other the Chimera XC, and then finally you do the structural analysis and see what you're looking for. So that's the overview of the cryo-electron microscopy, from the sample preparation to the structure determination. Okay. So here are some list of the softwares you can use for the single particle data analysis. So the most few years earlier, the Reliant is the most widely used the software. It still is used, widely used, but because of the speed issues, most of the people now they process their data in CryoSPARC. But still, most of whoever use the CryoSPARC, they still try to use the Reliant to compare their data to make sure whatever they get from the CryoSPARC, they also get the same results from the Reliant. So, and the EMAN 2, that's that's also another software suite for the data processing, and it can it's also very good for the Tomo data processing. iMode basically used for the Cryo-ET data processing, and CPN is kind of wrapper for all these softwares. So you can also use the CPN, but this CPN works very well with the specific data automated data collection software we call the Leginon, and then you can do the like live data processing, collection and processing together. So that's the good for that purpose. So now I'm going to move to the CryoSPARC single particle analysis. So here I want to show you how the directory, how the data processing structure works in the CryoSPARC. So you see, you have a data collection, then you collected the data, you get your data is ready, and then you do the motion correction first, because the data we collect is we collect as a movie, not we collect as a fractions. If you, let's say, like if you want to expose two seconds, we fractionate 2 seconds into 40 fractions, and then we save the images as a state. That's why we call the movie. And then motion correction, what we do in the motion correction, we have a protein particles. So we track the individual protein particles into the different frames, and then try to and measure the drift between the frames, and then we put them and then align them. That's what is called the motion correction. And then by doing that, we can avoid the drift during the exposure. So, and then after that, we do the CTF estimation. We call the contrast transfer function, and that's very important for the Cryo-EM data processing. And if you mess the CTF, everything will be messed up. So it's very important to have accurate CTF estimation. After that, you do the curations, micrograph curation. So in the micrograph curation, what you do it, you just you remove the bad micrographs and then use the good ones for the rest of the following data processing. After the micrograph curation, we do the picking. There is a multiple ways you can pick the particle. You can simply use the blob picker. If you have a template, you can use the template picker, and then you do the extraction. Extract the particles. What the extraction is, you pick the individual particles and then crop out the small images for individual particles from the large image and make a stack. That's called the extraction. After the extraction, we do the 2D classification. We align the particles, the extracted images in a 2D, and then classify them. And then we use the 2D classification to remove the bad particles. So that particles can be because of the air-water interface and denaturation of the protein. They can be because of the air-water interface, and some of the particles are damaged, so we remove that. And also some of the, there might be some huge conformational change, so you can also discard this and do the sorting using the 2D classification. And then afterwards we do the ab initio reconstruction to do the to get the 3D low resolution 3D model from the 2D images. And then we do heterogeneous refinement and homogeneous refinement. And after that, we do non-uniform refinement and then local refinement and post-processing to check uh, the, uh, the resolution distribution at different part of the map. And then you will get the final structure, and then you decide whether it have good enough resolution. If you don't have good enough resolution and you have good particles, and you can go back and collect more data and do the processing and combine them together to get more to get the better resolution. So the CryoSPARC hierarchy is specific for sample. So you can maybe you can go start the processing. So meantime, while it's doing processing, I will also explain this part. So we can go to the go to our CryoSPARC. So I hope everybody was able to log in and launch the CryoSPARC. So first is what we did. You need to create the project. So here I already created the project. You don't. Let's go back and create a new one. So you go to the here on the left side. You see that there's a box. If you click that, you will open up overview of all the projects, and you can see on the top is the projects. And if you already have created the project, you can just drop down and you will see the list of the projects. You can select that. But since we want to create the new one, you can just go to the new project. And when you click the new project, that's the green one, you can put the title here, for ferritin underscore test. And then you also need to define where you want to save your data. So you can Hey, Mike, what is the directory name? So you go to Scratch, then user, and then you can find your user.
For the shared data, it's Scratch training.
Oh, okay. But the results will be saved in their home their own directory. You can say. So this is the result of process the files.
Oh, okay.
Okay. So you put the scratch use /scratch/ user / find out your username. So mine is 12.122.665, and then you can just create the directory. You can select this the home folder, and then that's where it will store the processed file. You can also put the title for the workspace. So I'm saying the training to March 26. You can name whatever you like. Your sample. You can also put the sample name here or date or of the data collection, and then you say create. Now, if you go here, if you go, since I put both the title for the project and the workspace, so that's what uh, if you go here. So you have one project, you can create a multiple workspace. Uh, so to process the data, let's say you collect some data on one day, you process and you find out you need more data. You can create another workspace under the same project. So that's why it's have that's how it works. And under that workspace, it will create different jobs, and that jobs can be you can be exported into the different workspace. So now you have you can see here on top you have a project name and then workspace. Now the first step is we need to import movies or micrographs. So you see that here the list of jobs. Either you can use this one or you can go to the job builder on the right side and you can click here and just say import. You will see the list of the different jobs, available jobs. So I would say import movies, and then it will open up this tab. And here you can see that on the right side, it have a different options. So it will, you need to define where are your images or movies. So you click the folder, you will see this, and then you go to the this scratch planning. CryoSPARC, Cryo Center, Epofertin demo. And then under the demo, you see the movies. So these movies are just movie files I put on one folder, but if you real data, you will see the different files. So you need to select the one which have a fractions.tif or fractions.mrc, whatever the format have been used. But you need to know what are you need to select the file which have fraction stacks. So when you collect the data, you have a different file. One is just integrated single image. One is a movie file. One is just overview the JPEG. So you need to select the one that have a fraction. So I select the one and have a fraction. If you go all the way down on the here, you can put the wildcard here to select all the files, not just one. So I put the wildcard here to select all the TIFF files. So the TIFF files are selected. You also need to provide the gain reference file for the data collected. So this file will be provided by the center where where you collected the data. So here I saved the gain reference file. You can select that one and then select. So our another thing you need to know about the gain is whether the gain you need to rotate and flip the gain. So that's based on the camera, how the camera orientation used on the microscope. So our camera is well, while it's collecting the data, its images are flipped horizontally. So we don't have any defects right now. So all the defects are corrected during the data collection. So you don't need any defect file. But if you use the facility they provide the defect file, then you have to import here. Since our image our data during the data collection and the images are flipped horizontally, so we need to flip gain reference same as our images. So you need to click this flip X, and then we need to provide if the gain is rotated. Let's say your images are saved as after a 90-degree rotation. So it depends on the setup. So if there is a rotation, you need to provide how you need to put the rotation back. So you need to provide here the value, what is the rotation was used. Then you need to provide the pixel size. We collected the data in super resolution mode. They have a pixel size is 0.326. Acceleration voltage, it depends on the microscope, whether it was 300 kV or 200 kV. So ours is 300 kV. Then recent the newer version of the microscope, they have same especially if you buy if a microscope is from Thermo Fisher, they have this value is called spherical aberrations. That's always 2.7, but you need to make sure this is correct. And then you need to tell the software how much dose you use, applied total dose you applied. So here we applied the total dose 42 electrons per angstrom square. So you need to provide that value. And if you collected EER, then you have to provide this value, but ours we don't need it. And after that, you just say, okay, queue the job, and you will see showing the launched, and you will start it now running. While it's running, you can start another job. So the next step is, if you remember, like on the workflow, we do the motion correction. So there is a different options for motion correction, but in CryoSPARC, most efficient one is the patch CTF. Sorry, patch motion correction. So you select the patch motion correction, and then what you need to do is open up this job. You can simply click that. You select that previous job. Either you can use this to open it, or you can just simply hit the space bar. It'll do the same thing. And then you see that here is the list how many movies. You just drag them into the movies, and that's what you need from here. That's the here is the different parameters. You can see the number of movies to plot. We usually keep 10, and because if you want to, you can say okay, plot everything, but it take longer. So we just plot 10 and see how it goes, and then we say okay, don't plot, just process it. You can also select, let's say you have 10,000 of movies, you want to see okay how our data is. You can say define it here. I only want to process 100. I only want to process 200. So that will, even though here you have 10,000, but it only processed 100 and will stop. and give you the result. So you can do the quick analysis for how good is your data. But here we only have for the test we only have 25 movies, so we're going to do everything. And next important thing is crop factor. So if your data is collected in super resolution and you want to reduce the size, because you can see here our movies are 8,000 by 11,000. So the cropping you can reduce is actually the binning. You can bin by 2. So you can bin by half. That will make the image size 4K by 5.7K, and that will make the processing faster, and you can reduce the usage of the computing resources. And then we want to override the overdose. Let's say you have some pixels that have a dose more than 42. We applied 42, but somehow they got more than that. We want to override that pixel with 42. So you can provide, okay, 42. Anything more than 42 should be written as a 42. So that will give you more cleaner background. And you can also define, and you can see that you can also define the number of GPUs you can use. So here we only request one, so I'm just using one, but you can if you have 4 GPUs, you can increase the number of GPUs here, and you can use. So once you're happy with all the settings, you say hit the queue the job, and now you can see that it's launched. It's started because everything is ready. While it's running, let's go back. So here I want to show you why the motion correction is important. So you see that without, while it's collected, this image is on the left, top left. It's just integrated image without motion correction. So you can see that the image looks blurry, like there is a drift, the particles are blurry. But after the motion correction and integration, you can see the particle looks more crispy and have a better background as compared to the image on the left side. That's why it's important to do the motion correction. And this make huge difference when you do the processing. If you just use this image for the data processing, your resolution will be limited to 4-5 angstrom. But with this one, you can reach to the below 3 angstrom without any issue. And that's also another thing is also it also helps if you have this drifty images that have a drift. When you do the CTF, these are called CTF thorn rings. You see that it have astigmatism. One side you have a more information as compared to the other side. But for the motion corrected images, you can see the information is homogeneous on all the directions. So it have a better a chance to get high resolution information. So that's why the motion correction is really important. Okay, so you can see here, yeah, so you can see that it's measure the drift on X and Y, and then try to align them, move all the frames back. And here you can see that why it's called patch, because it's make the patches on whole image, and then it track the drift, individual patch, and then align it. So here is the graph how bad is the drift. Usually the drift for the 300 kV Titan Cryos is not usually it's not bad if your grid is good. So here you can see like most of the patches are just a dot. It means they don't have a very huge drift. You can see this better. And if you can compare here, look the images here, and also go back, look the images on the imported ones. You see that they looks like the fuzzy. But if you compare this image with the one with motion corrected one, you can see the particle looks more obvious and more crispy, more contrasty. So that's why we need to motion correction need to very important for the data processing. So now you see that this job is done. Next job is you can do the CTF correction. That's called patch. Again, we're doing the patch CTF estimation. So you can do. We don't have we can estimate the CTF at different part of the image, not just a whole image. So you select the CTF estimation, and then you have a micrograph here. You can drag the micrograph file, stack file from the motion correction job to the CTF estimation, and then same. We only want to plot 10. We don't want to plot all of them. You can again select how many you want to process, and then amplitude. Usually we keep these settings default. But if you want to change, you can increase this amplitude contrast to 0.1215 to check and get the better estimation. But usually 0.1 is good enough to get the good fitting. So again, you can select the number of GPUs here. Depends on how many GPUs are available in your system. And then just hit the queue the job. And this job is fast as compared to the motion correction. Depends on the GPU type. It takes around somewhere in 5 to 15 seconds per image. So here you can see that I guess this is the fast GPU, so it only take 5 seconds. You see 6 seconds. But if you're using the GPUs with lower memory, it can take 10 to 15 seconds each image. So when you're defining like how many, what kind of, how much resources you request, depends on how many images you're processing. You can roughly calculate what kind of a GPU you are using and how much data you have. Based on that, you can calculate how many hours you need. So as I mentioned, the CTF is really fast, so you can see it's already finished. Now we can do the manual in curation. Means we can discard the bad images. So you just type the manual. It will show the manual curate the exposure. Just drag the images from the CTF job, and if you know that parameters, you can put it here. But usually I go and queue and go and manually check what kind of parameters are good for this data. So they started running. This is interactive based, so you have to go there and then find out what is good. So you can see here total. It shows the total number of movies micrographs now, and how many are accepted right now, how many are rejected. So based on what most important is here is the focus. So you see the average defocus here, the list of the range of defocus. So we collected most of the data at lower defocus, so it's fine. If the defocus you find something is more than 3000, then you want to discard it. And another thing is most critical is the resolution. So you see that here, most of the images, our range is already 2.4 to 3 angstrom, 2.9. So anything beyond 4 angstrom, you want to discard that. But these are selected the test data, so you don't have to discard anything. So these are two things you need to check whether you have some micrographs that have very high defocus that will not help, and also some micrographs that have a low resolution fitting. So the low resolution means this number is higher. So anything above 4 angstrom we usually don't use for the data processing. So that's why you need to go here and then define these values. And then once you're happy with this, you can say done, and then it will save it will save the rest selected the micrograph. So the next part is now we have we did finish the motion correction, CTF estimation, and manual curation. So the next step is we pick the individual particles. So we go to there is a multiple ways to do the particle picking. So first we do, if you have large particles, or here is we use the blob picker. So blob picker is usually just like it's considered as a small, based on the dimension you provide it like a ball, and then it considered a small ball, and then based on that cross correlation, it picks the particle. So what do you need here? You need the micrograph. As a micrograph comes from the manual curation job. So you drag that to here, and then you need the blob. What is the diameter of blob you want to pick? So these are the apophthegm. We know the rough dimension of this. So I would say 100, 10, because the dimension is 140. So it's a 110 to 100, 150. So everything is covered. So the different orientations, different views. In some view it might be 140, in some view might be lower. So we want to include the range, so we can include all different kinds of different orientation for the particular particle. And here you can also select the separation between the particles. So usually one is good enough. It means the distance between the two particles will be at least 150 angstrom. So you will not, the two particles will not be picked twice, because if same particle was picked twice, you will have a hard time for the alignment. So you want to make sure there is no, you don't have a particle that's picked twice. So if you have a diameter that's one, that's the same as the one, means the same as the diameter of the particle. And number of mix to plot and micrographs to plot, keep it default, because we only have a number of micrographs to process. Here we want to check, make the template. So first I will say, okay, just process 5, and then say queue the job, because we want to test. This is the trial and error method. So you want to process a small fraction of the data and then see whether it's working. Then you go back and process everything. So now you see that it's done 5 micrograph. You go back, and next is inspect how good is your picking. And so inspect particle picks. And what you need here, you need the particles, and also you need the micrograph. So both are from the block picker job. You can drag both of them here, and then you can, if you know the value of NCC score and the power, you can put here, it automatically discard that particles. But here we want to check. So first we go to queue the job, and then we can select the we can discard the bad particles interactively. So if you go here, it's waiting for our response. So you can see here, you can particle diameters, you can adjust that 140, and box size you can adjust this. So if it's 400, okay. So if you see that it's picking quite well, it's really, it's a little bit off centered, but it's picking very well. But you see this here is the black stuff. We don't want to pick this. What we do it, we adjust this power here on the histogram. So the black, if you want to remove the black dark stuff, to reduce the power, you can see it's already unselected. And then there is some particle that's from the background. And if you see that if there is some that's selected in the background, then you increase the lower limit, you will see that that will be gone. You see that? Now this is the way you select the, okay, good particle. Another thing is also this NCC score. So here is the NCC score. That's also reduced the particle picked from the background. You can see that. So once you're happy, it's not necessary, it don't have to be 100% accurate for at this point, but as long as their text is secured. So I'm happy with this, even though they are not centered, but it's okay. So now you can see that once you hit this, you can see they are pegged. The next step is we want to crop out the individual particles to make the particle stack. So that's called extraction. Extract. If you put this, you will see the job list. Extract from the micrographs. So you select that job, and then here the micrograph accepted, and then particles accepted. You drag these two inputs in this job, and then you decide, you select how many GPUs or only CPUs you want to use. Here, when you extract the particles, you need to know the size. Since we bin the micrographs during the motion correction, so if you remember, when we import, we put the pixel size 0.326. When we bin by 2, then now our pixel size is 0.561. Oh, 651. So based on that, you have to find out what the box size you need to extract. So the box size, the rule of thumb is at least more than 1.5 times of the diameter of the particle. So we know that the apophiltrin is around 140 angstrom. So we want at least 200 angstrom. So you can calculate 200 times 200 divided by pixel size 0.651. So you can see at least we need around 310 pixels. So I would say three. I would roughly I usually use little bit larger. So people say it like 2 times. So I will use the 400, and I can bin them again to make the pixel size even higher, and make the data like the file size is smaller, and that will help to process the data faster. So we extract everything. Number of micrographs, you can here define how many you want to extract if you have more than that, and then you queue the job. The extraction is launched. You can see started. While it's running, you can should be done very quickly. And next step is we want to remove the bad particles from here. So what we do is we do the 2D classification. So we put the 2D, we'll show up the job list for the 2D. Select the 2D classification, and you need the particle stack. So you drag down the particle stack into the stack file, and leave everything here the default. You can adjust this to a little bit later on, but for now it just leave it default. Since we have only 1500 particles, so we can say just classify into 20 class averages. You can also define here what's the alignment resolution you want to use, but if you keep it default, it still is okay. You can also define here what the circular mass. So since we know it's 140 angstrom, I can use 160 angstrom. So to keep some wiggle around the particles. Okay, so and then final iterations. Sometime if you for this one is okay, but if you have small particles, you might need to change the online iterations. Usually the 30 to 40. That will help to better separation. After that, you don't need to change anything except the GPU number. Since we have only one, I'm going to use one. So you can monitor the job here. You can see it's already doing the classification. You can see quickly, because they're large particles, it quickly separate the bad ones from the good ones. And next job is, while it's running, we can build another job. We call the 2D selection. So easy 2D classification, select 2D class averages. What we need here, we need the particles from 2D class averaging, and also we need the template. So we can put it here, and this, you don't have to wait until this job finishes. You can submit this job while it's running, and once it's finished, it automatically starts the next job. So that's another good thing about the CryoSPARC. Okay, we can select here. Let's run. Okay, and we can go back and monitor this. So you can see now we already have some good class averages. It's almost done. Okay, so that's finished. This is waiting for us. Okay, so now you see that what we can do it, we can select a few because they are circular, so you don't have to. Okay, so let's say select 5 of these as a template. You don't have to select everything. So done, because I want to use this as a template to pick the particle. So you see that I selected 5, and when you select for the template picker, you need to make sure you have all the orientations, because this is the circular, these are like a round particle. So even though if I select only 2, it still is okay. But when you're doing your data, you need to make sure that you have at least one class average that represents different all different views. Now the next is to do the better particle picking. We do the template picking. So it's called the template picker. What you need here, you need the template. So that's our template from the selection, and we need the micrographs. So we can go to our curate job, and then pick up the accepted micrograph from here. Okay, what is particle diameter? 140. And then you can also define here whether you want all of them or you want to process some of them. So let's check 5, and then we will check whether it's picking, the picking is center. If not, then we can go back and change the parameters to make sure it's a picking, our picking is good. So you can see here now, we go back to inspect, and our particles, micrographs, queue the job, and here you will see they have the well-centered particles. So you can see here, okay, let's reduce some power, background picking. You see that how good is picking now. Previously, when we used the block picker, they are not centered. Now we have a template, so they are centered very well. You do again same thing. We don't need to do here, but if you picked everything, then you can do the same thing what you did previously to remove the particle pick from the background. Now you can see the picking is really good. Okay, so now we can say done. We can go back to the same template picker, and we can say, okay, clone the job. So you don't have to do anything. You just clone the job, and only thing you need to remove is 5. But we want to do everything this time. So you remove that and say, okay, run. This time it will pick up from all the micrographs. You can see almost done. Now you can go to the inspection, job inspection, you can go to the previous job inspection and say clone, and so you don't have to change the parameters. You can use the same parameter. Only thing you need to change is you need to change the input. So the input is you have to put it from the template picker that's used all the images. So that's the particles, that's the micrograms. And now you can do either you can put the value for the power from the previous job, or you can go and do it iteratively. So you can see here now, reduce the power to remove the particles from the background, or you can say ice, and increase the NCC score and also the power. And that looks good. So you can see that it's picked very well. Okay, you can go to different images here to see whether it's whatever the filter you use is good for or most of them. So you can see all look good. There's no ice picked. We have very few particles that picked from the background. That's fine. It can be sorted out during the 2D classification. Now once you're happy with that, you say done picking. Now you can go back to the extraction and do the same thing. You can do the classification. You see there is this extraction. You can do the same thing. You can clone the job to make it faster, and then you only thing again you need to change the inputs. So you have micrographed, accepted the particles. Now you see that we have 14,000 particles, and again you put these values and that submit. Once it's submit, it will extract all the particles. And meanwhile it's extracting, you can build the 2D classification job. Go to the 2D classification, select the 2D classification. I open up this job, and you can drag down the input from particle stack to the input for the 2D classification. You can also reduce this. I usually reduce to 0.8, 0.9. So it will filter out more background, and you can either keep it as it is, fine. And then you said submit. This extraction is already finished, so you can see it's already launched. So while it's running, it should not take too long. While it's running, we can build another the 2D selection. So we say 2D, select 2D class averages. What are the particles? These are our particles for the input. These are the 2D class averages, and we just say Q, and you will see here. Once the 2D classification finishes, the selection will start. View the job, or the status of the job right now. You can see that some of the 2D class averages are really good. And you can see some they're not very centered, they are filtered out slowly. We're already halfway. So here is the box size. Usually the box size is maximum defocus and 20 times into best possible standard the box size. But if you calculate is largely if a two times of the particle size, only good enough. Any questions so far? Okay, you can see that the job is done. Now you can go to the 2D selection, and we can select the one that looks good one and reach to high resolution, and then discard everything else. So you only have 1, 2, 3, 4, 5, 6, 7. Okay, so you can see them. The classes looks very good. If you do another round of 2D classification with this, you still can separate out some of the bad the particles. But here we just want to go through all whole procedures. So we want to go to the next step. So the next step is ab initio. So what is ab initio is we use this 2D information and align this particle into 3 dimensions, and then do the back projections to get the 3D 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 volume from this. So that's called ab initio. The no prior information. We get everything from the data. So you write type ab, it will show up the job list. Ab initio. What you need here, you need the selected particles as the input from the 2D class selection, select 2D class selection job, and then you can reduce this ab initio. You can also define how many ab initio you want. You can say I want 2, but if your data is heterogeneous, you can say ask for even more. But I will just ask for 2. How many particles? If you have millions of particles, you can say I only want to use fraction of the particle, let's say 200,000 to make it faster. You don't have, oh, you can also use all the particles, so that will serve as a classification, 3D classification as well. But that will be the slower. So here we don't have a lot of particles, so I will use all of them. And I'm trying to classify and get the 2 volumes and see how they are distributed. Okay, so we start. So this is the slowest job, the motion correction and ab initio, the two jobs that's at the slowest in this on the CryoSPARC. Any the processing software. So this might take a little longer. It's only have around how many? Only have around 8,000 particles, so it should not take too long. The good thing about the new CryoSPARC is they also put the tag. So you can view the 3D volumes here. So you don't in previous versions, we have to download the volume and open them in Chimera. But in the new version, you don't have to download. You can simply go here, volumes, and select here. You can see how they look. So this is just starting, so you don't see anything. It just simply looks like some density. You can change the threshold from here to go to lower threshold to have more signal. So usually if you click the follow latest, you will see what the iterations are running right now. You see that here is the 300 iterations. Usually like 1200, 1500, or this don't have many particles, so it might be stopped earlier. But usually somewhere around 1200 iterations, good enough to get the good initial map. So we will wait a little bit to get around that point. So it's 400 iterations. You go back to the volumes, you will see something better than previous one. You see that they start to come out the circular stuff. So you see that now it's have a ball, hollow ball like say already. This one looks a little better because you can see more features here as compared to the other one. It means this have either more particles or have a better particle. Yeah. So you can see here which one have more particles. So number 2 looks better. So you can see here there is no unused particles. You can also see that. Class 1 have a 7,000 particles, while the class 1 have only 1,000 particles. So this data looks like homogeneous. So most of the particles belongs to one class. So something like this is already look good to me, and it's good for the initial. But it will get a little bit better once once you have more iterations. This is 600. You can see now you can start to see some kind of features, secondary structure features. Looks like some helices. See that. You can see here 1,000. You can see the ball like structure, hollow ball. Okay, so it should be close to finish. So the next job is once we have a 3D ab initio, what the next job is to do the heterogeneous classification. You can do heterogeneous classification, or you can also do the 3D classification. So let's do the heterogeneous classification. And if you have just one, you can go and do you can do the heterogeneous classification, but it's not it's not necessarily you have to do it. So You can go back, you can run quickly the heterogeneous, we have time, so we can run the heterogeneous classification. So type the heterogeneous classification, and what you need here for heterogeneous classification, you need the particles tag, and also you need the volumes, initial ab initio volume. So you can select the particles that we know from the ab initio. You can use all these particles for the 3D heterogeneous refinement, or you can simply use the one that have a good number of particles in ab initio. You see that number one only have 200 particles left, and number two have most of the particles. Out of 8100, 7900 belongs to one class. So it's not really important to use these class and the particles. So I'm going to use this one. So that's this tag, and then you need to volume, and this is a heterogeneous refinement. It's kind of like a classification. So you can do the at least two classes, and you can import the same volume two times to fulfill this requirement, minimum two volumes. Or if you know that you have another confirmation for the same, and you have a two different confirmation, you can use the confirmation as the initial volume here. And you can change this refinement box. You can still use the C1, but we know that apoferritin have a octahedral symmetry, so you can use the O. But for now, we just using the C1. So usually for the heterogeneous refinement, we don't put the symmetry. We apply the symmetry at the last step. That will boost. Applying the symmetry will help in improve the resolution. But for the initial processing, I would not recommend to use symmetry if it is not required. So doing heterogeneous refinement, you can see it will be faster because of the number of particles. We have only few. So you can see we try to classify into two. Initially, it is divided like half and half. But over the time, you will see like one of the class will have more particle as compared to the other. If it is homogeneous, if it is heterogeneous, you will see the particles are different, distributed into different kind of like equally distributed into different classes. Depends on the severity of the heterogeneity. So the particles class one, it's already, you can see it's already put most of the particles in one class average. In another one, it only have 800, but first one we have 7100. So that's the another. Since we know that during the ab initio construction, we already classify into two, and we selected the particle that belongs to one class average. And when you do the heterogeneous, obviously they're going to segregate it into one class average. So that's exactly we are seeing here. This will here is the different plot. You see that it's showing the azimuth angle and elevation. So if your particles are distributed everywhere, then it's good. It means it's covering 360-degree Euler angles. But if your particles are segregated into one area, then means you have orientation issue. So you might have to find out the ways to collect the data differently to collect to collect all the Euler angles. So Euler angles means you collect the data let's have all orientation from all different view of the particle. Otherwise, when you do the reconstruction, the one the view that is missing will be missing into 3D reconstruction, and then your map will be incomplete. So another is to save the time. We can avoid the heterogeneous refinement, but you need to do for your real data. We can run the uh, non. You can run the homogeneous refinement. After this, you can run the homogeneous refinement. Do the homogeneous. What do you need? Again, you need the particle stack. So we can use all the particles from here ab initio. You can use all, no, not all. The particle belongs to the class 1 that have a large number of particles. And then we need the initial volume. So we can use the volume from ab initio job. You can also, if you have mask, you can provide, but it's not required. So I would usually use the mask created by the CryoSPARC. So I found that it worked most of the time better than if I provide the mask. So you can alignment, you can provide these value, how many final, usually do like 4 5. So what you do here, if there is no change in the resolution, or no change in alignment angles, then it will stop the processing. So, but if you want, okay, force it to run like 4 more extra iterations, then you can provide, okay, number of final extra processes. So let's say if I give 1, then even it's converged, still it will do 1 more iteration. So for now, I'm leaving it as a default. And then again, you can change the values. Some of the usually you run it into default first, and then if you see something missing or something not making sense, then you go and play around these parameters. So you go and say Q. Since we only have one GPU, and that one is already used in heterogeneous refinement. So you will see like my job is here. If you no, not this. If you go here, saying that Q, the GPU not available. But if you have 2 GPU, you using one for this job, you can use other one for this. Since here we only have one, so it's waiting for this job to finish. Once this will finish, it automatically start another one. So since we plan to not run this, so what you can do it, you can kill this job for now to restart the homogeneous refinement. And now you see that as long as the GPU become available, it started this homogeneous refinement. So homogeneous refinement usually give you the map, and the final resolution will be higher as compared to the heterogeneous refinement. So you can already see that high resolution information already start to come out. And since it did not see huge change into the different iterations, so it says stop, and you say that's what it's a final resolution. So now after the homogeneous refinement, you can run it non-uniform refinement, and let me. And this one is data is too little. So if you don't apply the symmetry, it will end up at very low resolution map, because overall the amount of data is not enough to reach high resolution. So even if you run this non-uniform refinement with the octahedral symmetry, you can see like right now is our resolution is limited to around 7 angstrom. But if you clone this job and restart this. In place of C1, run with octahedral symmetry. And since because it's octahedral symmetry, it means your data is 8 times more than C1 symmetry. So now you will see like it will give you the better resolution map and better map and also higher resolution map. So it's running already. So for these like heterogeneous refinement and also homogeneous refinement, you need to if you have a C1 symmetry, then you need more data. So you will already start to see, you have already seen that you can see that you have a better map. Even just in the second one iteration, we can see high resolution feature. So, and also here you can see the FSC, the Fourier correlation uh, plot, the Fourier correlation. So, and that tells you the how good is your resolution. So this Fourier correlation is the kind of same as the R value R value we do in X-ray crystallography. So it's do the same kind of processing. We divide the data into two, process separately, and find out the cross correlation between the two. And based on the cross correlation, you can define what is the resolution. So the FSC cutoff for this resolution estimation is 0.143. It's based on that where is the FSC cut the 0.143. That's the resolution limit for the process the data. You can already see that when I applied the symmetry, even at the small amount of data, we already reached 2.67 angstrom map. And if you go to the volumes, you can see it now. You can see the density from the individual amino acids, and you can clearly see the high resolution features. And next step is this is homogeneous refinement in using the octahedral symmetry, and now you can use the non-uniform refinement. So non-uniform refinement means it will consider a different part differently, so that if one part of the protein have some disorder, the resolution in other part will not be affected by that part. But in homogeneous refinement, it's considered as a whole. So if it have a distortion in one part, it might be affected on other part of it. So we can after this we can run the non-homogeneous refinement, and so this you can sorry, let me delete this and open another one, non-uniform refinement, and then use the input from use input for this job from using the output from the homogeneous refinement. So you copy drag all the particle size and use the volume in its volume. You can also use the mask here, but you really don't need it. And then do this. You have to change this to octahedron. And you can also add some final processes might help to improve some quality of the map, but usually it doesn't help to increase the resolution. So that's the non-uniform refinement. So individual part will be dealt with separately, even though it's processed together, but they will be treated separately. So as I mentioned earlier, if we have some problem on one part, it will not affect the other part. So now we have if you remember, we when we extract, we bin the particles by 2. We extract like box size is 400, and then we extract the bin by 2, make it 200. So our pixel size is now, as compared to the data collected, is 0.326. Now we binned by 2 times. So it's become 0.32 to zero point 0.6, and then we bin again when we extract it, it become 1.2. So that's why you see that here, our in FSC, the limit for the FSC cutoff is because pixel size, the cutoff for the FSC is 2 times of the pixel size. Here, our pixel size is 1.2 something. So the 2.6 resolution is to, and a cutoff is around 2.5, 2.45 or something in that range. That's why you see that this is, it don't go all the way to the down. So what you can do it, we can go back and re-extract the selected particles to higher pixel size, lower pixel size, and that will help to look these FSC curves more better. So while it's running, it should be finished very quickly. So we can go to the again. Uh, uh, we can extract them. Go to extract from the micrograph. Okay. We can use the particles, these particles from the homogeneous refinement, and we need micrographs. So we can go back here and drag that micrographs here. Particle placed here, and then we have one GPU, and then we can do 400. And if you remember, we put the 200 here, but we want to process the at higher. We want to reach to higher resolution, so we don't want to bin them. So now the pixel size is 0.651. Okay, so we extract them. It will wait until this job finished because we only have one GPU. Another thing you need to pay attention is FSC, and another is the Guinea plot. So the Guinea plot is showing the B factor. So higher the B factor is means higher the noise in the data. It means you use either you have a noisy data or your ice is thicker. So next time if you see like, okay, your Guinea factor is more uh, B factor is more than 200 or 300, you just simply go and try to make the ice thinner. That will help to increase the decrease the speed factor value, and also that will help to increase the resolution. So you can see that the particles are distributed very well in all in all the azimuth angles. So that's good. Okay, so that's already reached to the resolution limit, same as 2.67, as we seen in the previous run for the homogeneous refinement. We seen 2.67. So that's kind of a limit, looks like, at this pixel size. Okay, so maybe 1 or 2 more iterations, and another thing you need to look on your data for your data is these FSC plots should be the smooth. They should not be like up and down and up and down. If they are not very smooth, then there's something, some issue, like either you have some part of the particle that's missing the density, so it have like, okay, flip flop the FSC curve. So it means you don't have a good data. So if you see something, it means you go back and make the better sample and collect the better data. Okay. And you can go back again and look at volume. You can see that, clearly see that hydral symmetry. And if you look carefully this data, you can, even at 2.67 angstrom, you should be able to see some bulky side chains. So it looks like you see something here. For me, since the pixel size is large, so they're not very smooth, but you see that looks like some phenylalanine something ring, or it's tyrosine ring, either phenylalanine or tyrosine. So that's aromatic rings. You can see them. You can even see some kind of like some space in between. So that's a finish. You can go back, and as long as that GPU become available, you can see the extraction is extraction finished. So now we can run we can run non-uniform refinement with the smaller pixel size, and that should be able to increase the resolution. That the particle, you need the particle stacks, you need the initial volume. You can also put the mask, but it's not required. And make sure you put this symmetry information, and you don't need extra final process. Reduce the time. Okay, run it. This time you will see that this FSC goes to even lower resolution. Should be able to, because the pixel size is 0.651, so the cutoff should be 1.3 angstrom. But this once you increase and decrease the pixel size, it means you're increasing the image size, and that will also, it means you need a more computational resources as compared to the previous job. So it should take longer than the previous job. That's why you see that this is still reading the micrographs. It started. Just average of the initial volume we provided, running on local validation, and just close to it. It will take a little longer than the previous one. So previously we processed the data, the maximum resolution we got 2.64 with non-uniform refinement. So since we have a limitation on the amount of data, so the resolution is kind of limited. But if I can increase the, if I double the data, you will see that this resolution will quickly go below around 2 angstrom. So this is when we process all the data, around 3,000 movies for the same sample. We got 1.556 angstrom resolution from the same data. So here we got 2.67 just because of the lower amount of data. While it's waiting, doing calculation is not waiting. So we can go to some background. If you go here, just have somewhere you can here. So if you click here, it will show up the list of all the projects and also the project. And let's see, like this, and select this project, and then so here is showing the different list of the jobs. You can make them like just a list. So that's how you can show which job is running and the better view, how much time it how long after and how long each job took. So that will give you like overview of how much time you spend. And if you go another one is like preview. So you can see the flow chart of the different jobs. So what has been done, and if you can even export this image for the later reference if you don't want to save everything, like write down every step. So that can have kind of like your steps as you know what you did and what steps have been done. So you can just have somewhere it's option. You can save this the diff type of. So yeah, it's finished the first iteration. You can already see the second structure pictures. You see the high resolution one, and if you go to the volume, you not see the high resolution. It's still running local cross validation. So this is a little bit slower because of the larger image size. But this is the the local the whole procedure how you process the data in the CryoSPARC. And what else you need is You also need to verify. You also need to, like, usually if you look the CryoSPARC publications, they provide the colored map based on the resolution. So what is to do that? What you need to do it? You go to the local, type the local. You see local resolution estimation. So if you go the local resolution estimation, you can put the half maps here, and you can put the static mask here, and then you also need to provide what the step size. Usually, I would say usually zero point 0.5 I use, and FSC, what FSC you want to use for the threshold, and then you run it, and then it will provide you the files, two files. One is two files, and then you can open that file in Chimera and use the color tab on the Chimera, and then you can color the map based on the this information resolution estimate from this. So that's what they will do to color their map based on the resolution. Another thing, another type of refinement you can do it. So once this is finished, what you can do it, we call the local refinement. So there is two more, we call the local CTF refinement and local refinement. So you can do the CTF, local CTF refinement is going to do the individual particle CTF refinement. While in the local refinement, what it will do it will do the local alignment, not the whole particle alignment. So the most of the in some cases, if you do the local refinement, it will boost the resolution a little bit. It's not going to make a huge difference. It only, let's say you got 2.5 angstrom, and if you do the local resolution, local refinement, you might get to point like 0.1 or 0.15 unit improvement. But that's sometimes it's okay. But if you don't see a change in a quality of the map, then that's not really worth to run it. But if you see some change, you, it's worth. But usually what happens is you might see some like more better density for side chains when you run the local refinement. But overall, sometimes overall refinement even don't change much. But you might see the change in the densities for the amino acids or side chains. So now you can see that it's first iteration finished because of the size taking longer, and now you can see the volume that previously not showing. We have one output, so it's showing the volume here. So first iteration you can see just like a divided segregated density, but over the time it will improve. It will improve. Okay, so that's the and that should give you. You can see here already the FSC plot is 1 point more than 1.5 angstrom. So that's what you need to present. Because if you do go back to do the extract the particle at the full resolution, means pixel size is 0.326, then you will have, then it will take even longer, but your FSC will go 0.6 angstrom. And this should go like this, somewhere like this here, because this have 2.5 angstrom resolution. So this is cutoff. The blue line is showing the cutoff, that is 0.143. So that should go somewhere like this. And this should be the smooth line. Okay, and this, the B factor should be below, it should go below 100. And the particle distribution is should be everywhere. Okay, that's right now it's only using 486 particles. That's why the distribution is low. And as long as it's using more and more particles, it goes through the different iterations, you will see better resolution and the more particles are used. So that's the one thing. What else? I guess that's all for the CryoSPARC data processing. Now, let me know if you have any question for that. I can answer. Hello?
Thanks, Gaia. We're still here.
Okay.
Yeah, we'll have this recorded and available on our YouTube channel. It'll take a few weeks to process it, but you can check back in a few weeks. And our YouTube channel, you can access this from our main hprc.tamu.edu webpage. In the top right corner, there's a YouTube icon.
Thanks for the tutorial. I didn't get the license until like you're like halfway through the demo, so I couldn't really log in. But so if I have data already in a scratch, like how do I get that into, like, will that be visible if I start a session, or do I have to have that moved to another directory?
So this data is, you mean the data we processed here?
Oh, if I have my own images.
Oh yeah, you need to copy that images on clusters on your storage. You mean you can run it on the HPRC. So if you have account on HPRC, it depends on how much space you need. So you need at least depends on the data size, but usually for your own data, you need like couple of few terabytes of space on the HPRC.
Yeah.
So you can copy everything over there, and then you can here, if you go, remember when we create the project, you can direct the project wherever you want to save your data.
Okay, yeah, because I have it. It's in a scratch right now on HPRC.
You already have it on the scratch. Yeah, so you can select the scratch user and then your user name and wherever your folder. That's where you direct the path.
Okay. And I guess another thing we had, so I had a student trying to do this like last year, I guess, and things weren't set up. I don't think they were set up as well as they are now, but we had problems with basically the size of the data set and the amount of compute time that it needed, because we were trying to do reconstructions of whole bacteriophage heads, which are maybe about 85 nanometers in diameter, made up of about 1,000 proteins. So we were kind of running into, it was hard to do like the resolving, right? Because it needed like a lot of compute time. So I don't know if there's a way to cut down on that, like if you can do like part of the data at a time and then merge those later, or when you're doing the refinements.
So what you can do it, let me show you something. So what you can do it, you import, when you're importing the movies, what you do it, you can specify like here. Let me open the new one. So if you go here, job builder import, let's say you're importing movies, right? And what you can do here, you see that you don't import everything. So you import like divide your data. Let's say you have 1,000 images, right? Movies. You divide into 5 different groups, and then process individual group and do the 2D classification and process and do all the sorting, everything. And then you, from 200 movies, you find out the good particles, and then do the same thing for other groups. And then at the end, you only have like initially you will have like a few thousand particles from 200 movies, and but after the processing, you only have maybe you only have like few thousand. So the processing few thousand is, and then you can combine the data from all the different groups and do the 3D reconstruction from that. That's one thing. Another thing, you can bin it to, like I did a binning 2-3 times, right? Because your particles are large, you can bin 8 times, 10 times.
Mm-hmm.
Make them really, really small. And then once you sort out the bad one, you only have like you do the unbin, process the unbin data at last moment, like at the last step, to go back to high resolution information.
Okay.
Yeah.
And I guess another question I had was if there's a way, I don't know if we can do it in CryoSPARC or another tool package that, so if we have like picked particles, like say for a phage base plate, and we want to just pick out like a sub feature of that, is there a way to automatically like process from the, say like from the 2D classification step, like I want to just section out this feature and it'll go back to the original images and just section out those features?
Yes.
And then do it again?
Yeah, so what you need to do it, you need to, we call the particle subtraction. So you do the like a small process the small data set, and you have you make the mask, 2 masks. One mask is masking the density you want to keep, and the rest you want to discard, right? So when you do the particle subtraction, you provide the larger mask to subtract. So that will, when you extract them, so that will, the density that will be subtracted from the particle, and then you can reprocess the whole thing, do the whole procedure only for the part, the part you want.
Yeah, okay. That's something we might need because we have like these, the reconstructions are typically done with symmetry applied.
Mhm.
But then there's one feature I think that may not have any symmetry. So I want to like take that bit out and then redo it without any symmetry and see what it looks like.
Yeah, as long as it's not very small. If it is very small, then it might be have a hard time to align. But if it's not very small, like just then it should be okay.
Yeah, it's still, I think we're still looking at a feature which is a few, several nanometers, I think,
No, then should be okay.
in size. Yeah.
Yeah.
Okay. Thank you.
Okay, do we have any more questions? All right, well, thanks everyone for attending, and we're going to go ahead and end the session now. If you have any questions, you can send us an email to our help desk. You can find our address on our website, hprc.tamu.edu. It's help@hprc.tamu.edu.
But you might close
Yeah.
before we
Sorry.
pack up. So when we have we're running these CryoSPARC sessions here, and so when they're completed, is it important to delete them, or is it once it's completed, it's release the resources?
Once your CryoSPARC job completes within CryoSPARC, the portal app is still running. So if you're not doing any more processing, then you should go ahead and delete the job and release the resources.
Okay, so click the delete to get rid of it.
Yeah, but I mean, if you're working and it's at 10 o'clock and you run your job, obviously you're not going to get up at 3 in the morning and check your job and see if it stops. If it's done, you just wait to check it the next morning. And also, if you're working on something and you see the processing is taking longer than the maximum queue time, which is 2 days for the GPU queue, then you can request an extension for that job.
Right. Okay. But when we're running a job, we can only use a maximum of 1 node, right? Or will it spread across nodes?
No, currently we just it runs on one node. But we do have, you can select 2 GPUs, just not during the short course. I limited it to 1.
Yeah.
But in the regular CryoSPARC portal app, you can select 2. And if you still have a lot of processing, at times we do have 4 H100s on a compute node. If using 2 GPUs is not enough, we could probably add a configuration for the 4 GPU.
Okay. Right, thanks.
You're welcome.
Okay, so we
Thanks.
thank you.
All right, thanks everyone.